Welcome back! You've probably noticed that in the process of picking a P-type MOSFET for our specific application here, shown on the left, it wasn't so hard to find one that works, except for the fact that it's really hard to control it with the 0 to 5 volt Arduino signal that we have limited ourselves to. In a high side switch application, the source of this P-type MOSFET, which is that pin over there, is connected to the 12 volt voltage source. This means that in order for the MOSFET to be off, the gate voltage also has to be at 12 volts so that the VGS, or the gate to source voltage, is 0. This is because the gate to source voltage is what turns on and off a MOSFET. This isn't really possible to do since the Arduino only outputs either 0 or 5 volts. It doesn't go up to 12 volts, so the MOSFET will be on regardless of the Arduino's voltage. This is, of course, assuming that the threshold voltage of the MOSFET is within the typical limits like 1, 2, 3 volts. So what do we do here? Let's say that we've chosen this P-type MOSFET as our high side switch. So this is a NTF6P02 MOSFET. It's a P-type MOSFET, power MOSFET. It's got about 10 amps of drain current. Let's ignore the fact that this isn't 30% derated as per our initial rating. It's got a 20 volt VDS rating, so well within our limits of greater than 16 volts. The RDS on is significantly higher, so you can see P-type MOSFETs generally are not as good as N-type MOSFETs in terms of the RDS on. It's rated to 10 amps of drain current, as we already talked about. The operating junction temperature, the maximum is 150 instead of 175, so this is something we'll have to take into account. And the junction to ambient thermal resistance is somewhere between 71 to 160 degrees Celsius per watt. Next, we'll take a look and see that our on characteristics show a VGS threshold voltage of approximately 1 volt as the maximum. So when the gate pin is only going to be brought down to 11 volts, the MOSFET's going to start turning on, which is awesome. It's a very small threshold voltage. Again, we don't have to care about the incapacitance stuff. We really only need to know what we know so far. The graphs inside of the datasheet are all really useful information, but basically we've already validated everything that we need to know about this MOSFET. We've taken a look at our limits, and our only limit that we didn't take a look at is the VGS limit of plus or minus 8 volts. And this is going to come in handy for us in just a second here. Let's just do some quick math on our thermal dissipation. So assuming that our RDS on is going to be approximately 50 milliohms, we can do a little bit of math here and see that our I squared RDS on multiplied by the junction temperature, RTJ, is going to be equal to 10 amps squared multiplied by 50 milliohms multiplied by, if we go up and take a look, that thermal junction temperature limit was somewhere between 71 to 160 degrees Celsius per watt. And the notes down here say that when surface mounted to an FR4 board using a 1-inch pad size, so let's just assume we are using the best case 1-inch pad size, we get 71.4 degrees Celsius per watt. Now this gives us a delta T of, let's do the math here, 5 times 71.4 degrees Celsius per watt. Obviously, this is way too high, and we will not be able to remain within the junction temperature limits. So we won't be able to use this P-type MOSFET simply because we would burn it up. Now you can tell this P-type MOSFET is a surface mount MOSFET. It's not through-hole. So that's another thing to take a look at. Hey, the other MOSFET that we chose, this N-type one, it was not a through-hole. It was not a surface mount MOSFET. It was a through-hole MOSFET. And it had a huge heatsink itself attached to its drain pin. and it was much larger, whereas this P-type MOSFET is actually quite small. It is a surface mount MOSFET, and it is a lot smaller. Therefore, it's going to have a higher RDS on, and it's not going to be able to dissipate as much current. This is one of the good reasons why we always derate our maximum current specification and at least add 30% to it. So in this specific case, we're going to be hundreds of degrees hotter than what we need to be, and therefore we're going to have some sort of fan or heatsink, or we need to choose a different MOSFET. But anyways, let's go back to our initial issue, which is how do we actually drive this MOSFET? How do we control it with our current signals? Well, one way to use this is to use another N-type MOSFET, but this could be one that doesn't have to have a super huge package size, and it doesn't need to conduct a lot of current. So this specific MOSFET down here, this can be a very small logic level MOSFET, whereas the P-type MOSFET is the power MOSFET. We can use this N-type MOSFET along with a pull-up resistor here, 10K usually works pretty well, as a way to shift our logic back down to the N-type level so that the Arduino signals actually work. If the voltage at the gate of our N-type MOSFET is high, meaning it's 5 volts, then this transistor turns on and basically shorts itself, right? So that means that the gate of the P-type MOSFET will be at 0 volts, turning it on. Furthermore, if we turn the N-type MOSFET off by putting 0 volts at its gate, then this will be an open circuit. The resistor will pull this node up to 12 volts, and the P-type MOSFET will turn off. In theory, and in most of our applications, this works. However, remember how I mentioned that our VGS max is only 8 volts. This will not work for a specific application, and we will end up damaging our P-type transistor because of that limitation. Take a look at that limitation one more time. Our VGS max is plus or minus 8 volts. That means if we bring this gate voltage down to 0 volts, there's going to be a differential between the gate and the source of 12 volts. And that is going to cause us to exceed this limitation, which will kill the MOSFET. So what we need to do is protect this gate voltage from ever getting down to 0 volts. We don't need to get down there anyways because the threshold voltage is only 1 volt. In fact, if we were only at plus 10 volts, which is a 2 volt differential between the source, the MOSFET would probably still work just fine. So what we need to do is put another resistor of the same value in this circuit like this. This way, when we turn on the N-type MOSFET, the gate of the P-type MOSFET can only get as low as 6 volts. So if the N-type MOSFET is on, this node is grounded, right? Then this voltage divider will divide the 12 volts by 2, because that's what a voltage divider does, and so this node will only be at plus 6 volts. Then the differential between 12 volts and plus 6 volts is, of course, 6 volts, and that remains within our VGS max of 8 volts. So now there you go. We've successfully chosen a P-type transistor. Now you know how to select both an N-type and a P-type transistor for the purposes of switching on or off a load. But I have one more interesting topic for you. One other thing to watch out for is a MOSFET's internal diode. This is an internal diode between the drain and source terminals that is intrinsic in the semiconductor design of the MOSFET. It's always there. This diode has gotten me before, and it will get you if you don't remember that it's there. Information about this diode is typically contained in the MOSFET datasheet, but we should always remember that it is there. It's a pretty critical piece of information that many people forget. If you install a P-type MOSFET backwards, for example, in that initial switching application, then current is going to flow through this diode whether or not the MOSFET is on or off. Then the MOSFET will always be conducting current through its body diode, and you won't be able to shut it off. You will probably end up burning the MOSFET because the body diode will be dissipating a lot of power since its voltage drop is likely around 0.7 volts. What this means is that our 10 amp application, it would be dissipating 7 watts of power. that would certainly cause it to overheat. So don't forget about a MOSFET's body diode. I hope you've learned tons about MOSFETs. I've attached more questions and answers for typical interview problems to the resources section of this section, so please take a look. In the next section, we'll be talking about operational amplifiers.